So alhamdulillah rabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Good morning everyone. Happy Ramadan. Ramadan Kareem. Inshallah for today we can continue our class lecture. Oh, sorry, I need to send this. We're moving back to chapter 1. They have one subchapter we will not cover yet. So my planning should be last week, but I have some difficulties last week, so I need to postpone for this week. So last week you already learned about superposition on chapter 2. So for this session, we're going back to chapter 1, and we discuss about what we call as a complex function. And for the attendance, using this, they will capture your attendance automatically. So I will not send you any form, because when you attend here, so automatically they will detect. So they will capture all the attendance. Anything you can ask me, please send through the Q&A. Okay. I'll try to answer from anything related to the subject. And then for this week should be week number 4. Next week we'll cover chapter 3, damping oscillation. I will upload a video to goals. And week number 6, few before Raya, that will be your test. Your test will be on Tuesday, 3rd May. Sorry, 4th May. So objective 20 marks. The details will be uploaded goals. Actually, everything the goals already. The topic will be chapter 1 and chapter 2 only. So don't worry. For next week, damping will not include into the tests, but it will include the final exam. Okay, let's move to what we call as a complex function. So we start now. So complex function. So here, if you have a vector, wait a minute. Okay. If you have a vector z, so equal to x plus j y, for this kind of direction, which is this will be x, theta, y, and this will be z, and that will be the vector here. Okay, so this is what you usually make before the vector, especially in mechanics. But they have introduced what we call as a complex function here. So what is relevant? Okay. The meaning for the vector for j, or the certain books or reference, they're using I. Okay, and certain books are using J. For science, majority use J, especially for engineering we use J. But for our case, we will continue using J because I sometimes will represent the current of electric, is it? Current. And wave related to the RLC circuit, so related to the current. So sometimes it's confusing, so we maintain to use J here. So for this function, J represents the clockwise. Okay, J is a clockwise. Okay, because J is a instruction to perform a counterclockwise rotation, usually for the 90 degrees of 90 degrees upon whatever it precedes. Okay. So by represent J, so J is a indicator or instruction. Okay, that's that. Y is actually is a counterclockwise for the delta here. So that will be the physical meaning of the J. And from this, we call it X and Y is a real part. But when we have J here, this both we can call it as a imaginary part. Even though Y is a real part. So because they have a reality versus the imagination, so that's why Z become a complex function. To explain about J, actually it's a very long story. Even they have some notes you can find from through online to explain about the history of I or J itself. So, but I will not explain this here. So it goes straightly to the application of this J. So here, what happened in mathematics? Okay, we define J itself. Okay, we define J is a square root minus 1. Okay. So that is something unique about J because when we dealing with the square root, okay, example square root 4 can get 2, 4 can get 2, square root 2 can get 1 point something or something. Okay, so they have a value, but square root negative, okay, is something that we cannot solve. Okay, so that's why they represent, okay, with J. To get the value, usually can double, okay, J square, you can get the value is equal to minus 1. So that will be mathematical part, and it's really effect, especially in the wave also. And you will meet this also in the quantum mechanic, okay, to dealing using the imaginary part. So later we'll explain how to use the imaginary part for solving the to solve calculation, okay, of the wave and vibration. So for this moment, okay, you need to remember that J or I, okay, for this case we're using J. Okay, maybe sometimes we made for another subject something using I, but if we call the I is J, okay, Z is a complex function, I is J is a complex number. This is a complex number. the complex number itself, okay, j is equal to square root minus 1. Okay, this is something that you need to remember. And another one you need to remember will be z is equal to x plus g. Why? Sometimes in certain book using c is equal to a plus jb. Okay, doesn't matter. So this is a basic equation for the complex function. So okay, this will be the function for the complex. And okay, and then why is this important? Okay, we need to check through the related to the what we call as a complex exponential. So this next will be the complex exponential. Complex exponential. Okay, exponential. Okay, when they deal with exponential, they have what we call as a exponential e, power of a certain here. Okay, so this will relate with this exponential. Before we go here, we can check from this triangle. We know that for x here is equal to cos theta. Okay, x cos theta is equal to x over the magnitude of z. So it means that x is equal to magnitude of z cos theta. And for y is a magnitude of z sin theta. And this this will related to here. Okay, I will explain later. So first, the complex function itself, right? They have what we call as a series expansion. Okay, and here I'm not sure you learned Taylor's theorem. If not, you will meet when you study the mathematical physics, Taylor's theorem, or we can call it as a Taylor series. I think from Ahmad they call as a janjang. Okay, janjang arithmetic. They create the list of a series to the certain of the pattern. They have patterns that creates a series. So Taylor's theorem, the theorem for the Taylor itself is the function of fx, so equal to f. The value of x is 0. Okay. Oh, sorry. Equal plus x differentiate. Okay. Sorry, differentiate the function of a o 0, and then they have x square over 2 factorial f double division, and then there are plus. So maybe around x3 3 factorial. Okay. F 0. Okay, they have continue. So f prime here is the differentiate. Okay, means that they differentiate the function of f 0 over the x. So this will be the Taylor's theorem or Taylor's series. So for sin theta, Taylor's theorem is very good to relate with the trigonometry. For sin theta, we can put here f naught, f0. So for f0 means sin 0. Sin 0 is a 0. So it will be 0. And then plus x f prime 0. F prime 0 means that differentiate sin theta. Differentiate sin theta, we can get cos theta. So cos theta is for cos 0. Cos 0 is equal to 1 and x is a theta. So we can get here value of the theta, and then the continues with 0, and then we have here theta power of 3 over 3 factorial. If you confuse what is 3 factorial, 3 factorial is equal to 3 times 2 times 1. 4 factorial, 2 factorial, something like that. And then we have plus theta 5 over 5 factorial plus, you can continue. Next will be cos theta. For the cosine is equal to 1 minus theta 2 over 2 factorial plus theta for 4 over 4 factorial plus. Okay. And since that we know that x is cos theta, y sin theta, so we know that z, okay, is equal to x plus jy. So we can combine this both equation for cos, because this is a cos theta plus j sin theta, and we just avoid the z as a part of the it's like the value of the z itself, okay. And so what happened here for cos theta plus j sin theta is equal to, we combine both 1 plus j theta sin theta, okay, 0 kita avoid je, j theta, and then minus theta 2 over 2 factorial, theta 2 over 2 factorial here, and then plus, minus theta 3 over 3 factorial. For sine they have j, so j here, plus theta 4 over 4 factorial, and then you have plus theta 5 over 5 factorial j. Then we can continue here. So this is some tricky here. So we have 1 plus j theta, it's not a problem. So just to remove the negative here, negative 1. So negative 1 is equal to j square. Remember, okay, j is equal to square root minus 1. So minus 1 is equal to j square. So we can have here j theta square over 2 factorial. And then we have minus j. What happened is this minus j. So means that minus 1 times j. So minus 1 is equal to j. So j times j, we can get j square. Okay, minus 1 is equal to j square. So we have here j power of 3 equal to minus j. So here we can get here plus j theta 3 over 3 factorial, and then we have plus theta 4 over 4 factorial, okay, plus finally can get the basic of the series itself, which is j theta equal to n factorial power of n. So if n is equal to, you can get 2 over 2 factorial, 3 over factorial. So that will be the related with that. Okay, so this function is related to the exponential. So cut it short. So the value will be the exponential j theta. So this related to the exponential j theta. So exponential j theta is equal to cos theta plus j sin theta. So this will be another equation that you need to remember. Okay. With another one, j is equal to square root minus 1. You need to remember. And another one will be z equal to x plus gy. So here you can get the exponential j theta is equal to cos theta plus j sin theta. And this is what we call as a Euler relation. So if you have any question, you can ask. Okay, just play around with the Euler equation. So if we have here exponential j omega t plus alpha, so you can get here cos omega t plus alpha plus alamak. Okay. Plus j sin omega t plus alpha. So this is a function of the cos omega t. Okay. You can give something here. If we have a in the front, okay, amplitude. So this will be the a, and this one also we have a at the back. So that's something interesting about this function that we can use in wave evaluation. So why is similar? Before this, if you remember, when we dealing with the simple harmonic motion for pendulums and mass spring system, so after we define the MA or KX or everything, okay, and then we have the theta, cos theta, sin theta, everything, and then we have get a one equation, and then we define the value of x itself, and usually we put the value x is equal to a cos omega t plus alpha, or sometimes cos omega t. Sometimes x is x naught. So this what we call is this is only the real part. Real part. Okay. This is equal to this, the real part. And when we start dealing with the damping, there will be a imaginary part. So any question? So we continue for the application. Okay, the application in the simple harmonic motion. Okay, before we go to the example. Here the simple harmonic motion for mass spring system. Mass spring. Okay, we have sorry, we make the ticket here. Okay, so they oscillate something like this. We have mass m, and then the spin constant will be k. So if you remember, we have here ma is equal to minus kx. Okay, and ma is plus kx equal to 0. And then we know that a is a double depreciation of the x. So we have a m d square x of dt square plus kx equal to 0. This is repeated for the chapter 1, first chapter. So we have here d square x over dt square plus k over m x equal to 0. So we divide everything with m. So this is the equation. And then we define x. So right now we can use the value x using the exponential. So we define x, okay, which is the real part of the z, okay, because it doesn't have the complex function here, equal to a exponential j omega t. So we know that exponential j omega t is equal to cos omega t plus j sin omega t, something like this. Okay. So when we depreciate dx over dt, the velocity itself we have, okay, so you need to remember a is a constant, so it doesn't change. When we differentiate the exponential, it will maintain exponential j omega t. And then they differentiate inside j omega t, because differentiate dx over dt, so differentiate j omega t, you can get here j omega. Okay, so means that we have a j omega x. This is x, Okay. Next, double differentiation. For double differentiation, we differentiate this. Okay, we differentiate this. And differentiate over t. So again, j omega a become j omega a is become constant. Okay, doesn't have t function here. When we differentiate exponential j omega t, exponential will maintain, will not change. And then the differentiate inside j omega t, they will be times the j omega again. So what happened here? J omega square. So we have a j square omega square a exponential j omega t. J square is equal to minus 1. We have here minus omega square. And then we have here a exponential j omega t. Sama. It's the same thing here. So we have here x. So we can put this value, d square x over dt square is equal to minus omega square x plus k over m x equal to 0. And then we bring here to the right, we have here omega square x equal to k over m x. We can cancel x here. So finally you can get the omega square is equal to k over m. So it's similar to what we have discussed before, but we are using the exponential. And it's very important to use this, especially for the damping, because the damping, they have another parameter. And I think it's quite difficult to solve it using the cos and sine only. So this what we call have omega is equal to square root k over m. And convert to t. So that will be the how to use the exponential in the simple harmonic motion. So let's check if you have any question. I think everyone can write their question here. Okay, from everyone can use the Q&A. All right. If you have any problem, you can send here, or you can send through WhatsApp also. I will check from through WhatsApp. Tak clear ke apa ke? Alright, so continue to the tutorial for using the tutorial that I've given to you. Goals. Let's check is it I can open or not this here. Tutorial. Spesifik ujian. Okay. Alright, tutorial here. So for the tutorial, we have z equal to z1 and z2. And we define z is equal to a plus ib. Mana hilang soalan ni? Oh, sini punya. Alright. So right now, we have z equal to z1, z2. times that 2, okay. Z1 is equal to A plus JB, A plus JB. Tu selalu saya pun sendiri selalu tukar. Alright, so Z1 is equal to A plus JB, Z2 is equal to C plus JB. A and the B is a real part, C and D is a real part. C and D is a real part. But because they have J here, so this will be the imaginary part. So that's Z1 and Z2 is a complex. Okay. So the complex function, dia tak kena Argentina, okay. Complex function. So become complex. And then what we try, actually try to prove. Okay? So right now we have show that the length of Z is the product of the lengths of Z1 and Z2. So length of Z, remember this drawing, theta, the function of Z, Y, and X. So we know that Z vector, okay. So to get the value for Z, so means that the X square plus Y square square root. If you remember the vector. Okay. So you have a Z is equal to square root X square plus Y square. So this is vector to get the value of Z. So that will be the length of Z. But right now they have Z1 and Z2. So means that Z, okay, or is the product of the length of Z1 and Z2. So product of length of Z1 and Z2 means that Z1 times Z2. So it's equal to Z. So that will be the theory. And we need to prove that. And then we have here we can do this to get this value first. So first will be Z equal to Z1 times Z2, means that A plus JB times C plus JD. So A times C, AC, A times JD, A, JD plus C times, JB plus C. Okay, C, JB plus JB plus JD means that J square, B and D. So C square here, J square. J square is equal to minus 1. So we have here real part, imaginary. So this become the real part. So we have here AC minus BD, since that J square is equal to minus 1. And then plus JAD plus BC. This one, JAD, JCB, so factor J. So this will be the total of the Z, when Z times Z1, Z2. So right now means that you have because we have here, sorry, need Z1, okay, Z1 XY. So that right now we have for Z, okay, so Z is equal to, right now we have ACBD, so means that the Z value here, so we have another angle here, so means that AC minus BD times AD plus BC. Okay, the value, because this one is Z1, and then we have another Z here, Z2, vector Z2, theta 2, this one theta 1 equal to C and D. So resultant, we get the value Z here, and Z is equal to AC minus BD, AD plus BC. Now what we can do, Z square. Okay, so we have here AC minus BD square, and then plus AD plus BC square root. J will not count here because this is a vector. We try to find the value of Z. Okay, we try to find the length of the Z. So okay, AC square plus BD square plus, okay, just darab je biasa. So finally you can get here is a AC square plus BD square plus AD square plus CB square. Okay, this for the Z factorial for Z1 times Z2. Okay, for this, for the Z, magnitude Z. Okay, show that length. So length will be a magnitude of Z. So right now we try to find the magnitude of Z1, the magnitude of Z1, and also the magnitude of the Z2. And then we try to times both magnitude of Z1 times the magnitude of Z2. Is it we can get this value? So right now we have here A plus JB for Z1. For Z2 we have here C plus J and D. So for A plus JB, so this one is sorry, this one for equal to Z1. Okay, Z1 is equal to, okay, so to get Z, okay, the modulus of Z1, A square plus B square square root. For Z2, so equal to C square plus D square square root. So right now Z1 times the Z2, the magnitude of Z1 times the magnitude of Z2. So we have here square root A square plus B square times square root C square plus D square. So both are square root. So we have here square root A square plus B square times C square plus D square. Both are square root. And finally, you can get here A square times C square, A square, C square, A square plus D square plus B square, C square plus A square, D square plus B square, D square, B square, D square. So we want to see, is it similar? A square, C square, same lah. AC square. BD square, BD square, we have here AD square, A square, D square, okay. C and B, okay. So finally you can get, so it proved that Z is equal to Z1 times the Z2. So it's a proved, because we can get this same value here. All right. Question B. Okay, move to the question 1B. Okay, for 1B, show that the angle between Z and the x-axis, okay, Z with x-axis, okay, angle ni lah, is the sum of the angles made by Z1 and Z2 separately. So, okay, we define as Z, angle for Z and x-axis is a theta. Okay. So they want to say that it's equal to the angle made by the Z1, theta 1 plus theta 2. Sum of the angles, okay? jumlah angle for Z1 which is theta 1 and Z2 theta 2. So this will be the B. How to do this? Again, Z1 is equal to A plus JB, theta 1, A, B, and this is Z1. So tan theta 1 is equal to B over A. Tan pertengahan bersebelahan, okay, B over A. So convert to the arch tan, okay. So we can theta 1 is equal to arch tan or tan minus 1 sama B over A. Next will be Z2 equal to C plus JD. So tan theta 2 is equal to D over C, okay, because this Z2 CD. So this one will be theta 2. So tan theta 2 equal to D over C. So theta 2 is equal to arch tan or tan power of minus 1 D over C. And then so here from here we can get theta is equal to theta 1 plus theta 2. Okay, we don't find the theta yet, but for this equation means that the arch tan B over A plus arch tan D over C. And then they have a value or the equation, okay. This given for the trigonometry for tan, okay, for the arch tan or tan power minus 1 x plus alpha plus tan minus 1 beta, so is equal to arch tan alpha plus beta over 1 minus alpha beta. So this will be the equation. You can find it from books, okay. So here what we can get here means that tan minus 1 is equal to B over A. So B over A is X here. B over A plus beta here is D over C over 1 minus BD over AC. Since that alpha times beta means that B over A times D over C. Just rearrange inside to make it easier. So means A times C, we can have here BC plus DA over AC. We have it here 1 over BD over AC. We can bring here AC below. And this one also is equal to AC over AC. You can get here. So if both AC can cancel. So what we have here is BC plus DA over AC minus BD. So finally you can get is theta is equal to tan minus 1 BC plus DA over AC minus BD. Is it correct? So we can prove this because we already have this equation. Oh, sorry. We have already this equation. Okay, this. So if you can check from this equation, can we copy this? Okay. Bring here. Kena bawa ke bawah. Alright. So from this, so the theta, okay, theta here, tan theta here is equal to AD plus BC over AC minus BD. So means that theta is equal to H theta, okay, AD, okay, senang, AD plus BC over AC minus BD. So you can check here is equal, okay, this is similar, so it's proof. That's the angle for Z is equal to theta 1 plus theta 2. Right, so this will be the question number 1. And I hope from here you can continue to for the question number 2. Little bit similar is that they change to, instead of Z1 prime times Z2 become Z equal to Z1 over Z2. Okay, so it's a little bit different, but still it's a channel for you to answer this. So you have any question? All right. Okay, if you have don't have any question, you can continue to complete all the tutorial. Because the chapter 1 majority of the tutorial will be related to the complex function and not the simple harmonic motion. The simple harmonic motion is the application, yeah. So you need to use you need to know how to use the exponential I theta and how to use the complex function. All right, and example question number 6 of the tutorial, you can see that using the Euler Relation, yeah, and try to prove. So this will be complete, okay, of chapter 1, and then you need to know how to convert from exponential j theta to the cosine theta. So I already show here. So next week video, or you can check from Ghost, you can continue for the damping oscillation. Means that instead of example mass spring system, if you have a mass spring system here and it's oscillate up and down, K and M. So we imagine that the simple harmonic motion doesn't have the friction, so will be no friction. Okay, so no friction, and we assume that they will continuously oscillate, something like this. Means that when we have the oscillation, it becomes something like this. Okay, and continue with the same amplitude. Okay, but of course in real time it's not happen like that. They still have the friction, and the amplitude will reduce by time, and it take time. So when damping means that we can put here for the experiment, and we can put some liquid here. It's not just water. So what happened when we oscillate this mass spring system? It still oscillate here, but after that they will reduce. Something like that. Okay, so then the reducing here because they have what we call as the decay parameter. Still the solution, you need to use the what we have learned before, which is MA equal to minus KX, and have another function which is minus BV, which is V is the velocity and B is the friction constant. So this will be discussed later in the next video. You can check through goals. Because of this, so why it's very difficult to use cosine solution that we learn first. Because example, we put the value x, okay, is equal to a cos omega t. We differentiate dx over dt, which is equal to v. We can get here differentiate cos. You can get here minus a omega sine omega t, or to make it simpler, we cannot cancel it. And then next, double differentiation, the acceleration, d square x over dt square. Convert differentiate sine to cos omega t. Differentiate inside, we bring omega at the front. We have here omega square, and then we have here minus e. So what happened is we put everything here. So replace, okay, I changed this to the something that we're familiar before. We have here m. A is d square x over dt square. We bring kx to the left plus kx. We bring bv to the left plus bv, which is v is velocity, d square x, dx over dt. So it's equal to 0. Rearrange here, we have d square x over dt square. Divide everything with m, okay, and then we have here plus b over m dx over dt, and then we have here plus k over m x equal to 0. So ni saya susun balik, just rearrange. Imagine that here we have d square x over dt square, substitute, okay, we try to substitute. D square x over dt square is equal to minus a omega square cos omega t, and then plus b over m dx over dt is a omega sine omega t, so minus, so we can change to minus a omega sine omega t, and then plus, so I bring below, k over m x is a cos omega t equal to 0. So right now you have cos and sine, so it's very difficult to solve this equation compared to what we have just for the simple harmonic motion. Because simple harmonic motion, we doesn't have this value, so automatically cos omega t and cos omega t you can cancel out. That's why we need to use the complex function. And for the complex function, you can check through video how to solve this. Okay. So lastly, you have any question? Again, to remind you that we have mid-semester. So we have mid-semester test, okay, ataupun test 1. I already mentioned to you, it should be chapter week 6 before Raya, and then you need to submit also your assignment, so that when you come back to SIM, you can focus on the lab and also for your final exam. And I believe that they have a lot of assignment from the subject. So for the test, the topic will include only chapter 1 and chapter 2, which is what we have learned today, the complex function, simple harmonic motion, also the superposition. And alhamdulillah, they will be objective, so I think the question is not very difficult compare writing, because writing you need to derive and prove. But for the online objective, you doesn't need to prove too much, but I think more related to the complex function. So try to do the tutorial. Yeah. So do you have any question? Last, before we conclude for today's session. So already reached 1 hour. Okay, check from WhatsApp. So, and the attendance will collect through this system. The system should be capture your attendance automatically, because every one of you will already sign in. Okay, so walaupun ada masuk last minute, Hopefully you can get a lot of understanding of this topic, and this will be the crucial part. That's why I make a live session rather than just a video. So, okay, thank you very much. We see you again next week. Okay, next week will be on a video, already made the video, and then next another week will be the final test. Okay, so thank you very much. Assalamualaikum warahmatullahi wabarakatuh.